As a review, we've already talked about what the difference is between a research and a null hypothesis, right? So a research hypothesis is the statement of the predicted outcome. What do you think will happen based on your review of the literature, and maybe based on pilot testing, etc., 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 right? Any pre-existing knowledge usually will feed into what your research hypothesis is. The null hypothesis, or the HO, is mutually exclusive to the research hypothesis, and it's going to state that there will be no effect or no relationship in terms of your independent and dependent variables. Okay. Now, hypotheses have directions, which is great. There's only two that you have to know. There's a non-directional and a directional hypothesis. The non-directional hypothesis is what we will use in this class, so you can just know the difference between directional and non-directional, but know that non-directional is what we practice. And basically that's saying that either your means of two samples, or maybe if you're looking at the mean of a population and the mean of a sample, they're either equal or they're not equal. Whether one mean is greater than the other, it doesn't matter. If it's less than the other, it doesn't matter. They're just different. Okay, so non-directional hypotheses are just emphasizing, is there a difference between the means of the groups that we're interested in looking at? Directional hypotheses are going to be the opposite, where you are arguing if there is an increase or a decrease based on the intervention that has been applied. Sometimes this might be, we want to see if people improve their flexibility measurements based on a certain stretching program. We want to see how much weight people lose based on this diet, right? Those are specific directions that you think, right? Your predicted statement is saying, I think this mean will be greater than this mean. So again, the null hypothesis is going to be mutually exclusive and is always going to say that the means are equal or the opposite of what you predict will happen. So if you think that mean 1 will be greater than mean 2, the null hypothesis would say that either those means are equal, so there is no effect of your intervention, or mean 1 will actually be worse or less than mean 2. Okay, so they have to be mutually exclusive. But notice that the null hypothesis always is going to have some degree of argument that the means are equal to each other, or that the comparing groups that you're looking at are not different from each other. Remember that the null hypothesis is the one that is statistically tested, though. So keep that in mind. Okay. Again, non-directional hypotheses are used in this class. We're not specifying the direction of the difference, but we're just acknowledging that there could be one. With these hypotheses, they are associated with certain types of tests. For a non-directional hypothesis, we call or associate it with a two-tailed test. And remember, tails are in reference to kind of the end regions of our distribution. So you can think, if we're not specifying a direction, we're either guessing that a sample mean could be greater or less than another sample mean, we're looking at two tails, either above the mean or below the mean, right? In which case we have to split our alpha in half. So instead of alpha just being on one side or another, we say this is our level of confidence. Let's say maybe it's 95%, okay? Which means 95 or 100 minus 95 is 5%, or 0.05. If we divide that by 2, we get 2.5%, or 0.025 in the area under the curve for each of these alpha regions, right? But in either case, non-directional hypothesis is not specifying a direction. Therefore, we have to account for regions of rejection on both the upper and lower ends of the mean. Okay. Usually we're going to use two-tailed tests when a relationship or an effect is unknown. When we're looking at the literature, we can't make a decent assumption based on logical reasoning. In contrast, a one-tailed test is going to be associated with directional hypotheses because you are arguing that if this distribution represents our population, let's say, and we take a sample and we do something to that sample, that the sample has been collected from the population, but we intervene with them in a way, and we want to see if the outcome that we're measuring changes as a result of that intervention. Where that sample mean lies on this distribution, if it's based on a directional hypothesis, is going to be either one end or the other. Okay, it's not both, or it can't be both. So remember, directional hypotheses are arguing a certain direction. So let's say that I think my sample mean will end up being above the mean as a result of my particular intervention. My alpha region would then be on this side, and my level of confidence would be from this area kind of to the left, right? And the reason my area of rejection is over here is because if we have our sample mean land in this area of our distribution of our population, we can be pretty confident that that mean is no longer within our estimation of where our population mean should be located. So that would be an example if we predict that our sample mean is greater than another sample mean, or if we know the population mean that it's greater than the population mean. We could also have the other direction if we argue or in our research hypothesis that our sample mean is going to be less than our expected population mean or our actual population mean if we know it. Okay, but one-tailed test only has one alpha region. Two-tailed test has two alpha regions. The way that we calculate alpha is the same. You just have to remember in a two-tailed test you split alpha in half. Because the amount of error you're willing to accept is still going to be, like if we use a 95% level of confidence, that the amount of error you're still willing to accept is still going to be 5%. It's just going to be just evenly distributed in each tail. Okay, so we'll often use one-tailed tests when we know a current relationship or we have an established effect within our literature. So how do you know when to accept or reject the null hypothesis? This is where it gets fun. So we calculate our p-value, and then we compare it to alpha. Remember, alpha is unchanged. It is set a priori. So let's say our alpha is 0.05. We have a sample, we do some calculations, we end up getting a p-value. We compare that p-value to alpha, and then based on that comparison, we can determine if we had too much error or there was little enough error that we can accept that an intervention actually worked. Okay, so if p is greater than alpha, that's indicating that you have a large degree of error, or you have more error than you're willing to accept, meaning that error could have potentially played into the results that you got, right? Or maybe the intervention didn't work for some reason. So if there is a large amount of error, typically we're going to want to stick with the null hypothesis, right? And say that the intervention didn't work, there was no effect, there is no relationship between these variables, there's no significant difference. Okay? So if p is greater than alpha, you have more error than you're willing to accept, you have to accept the null. Because the null is like the innocent until proven guilty concept, right? The null is true until it is proven wrong. On the flip side, if your p-value is less than alpha, in other words, you have a calculated estimate of error that is less than the amount of error you're willing to accept, you can reasonably assume that the intervention worked, right? Or that you have a very small amount of error that could have intervened with the results that you got. So again, if p is less than alpha, we reject the null hypothesis. So that's why we call this area the region of rejection, right? The level of confidence is where we are confident our population mean exists. Region of rejection is kind of the area in which we can reasonably assume that the intervention changed our sample enough that they are no longer associated with this population, or they are different enough that they're likely needed to be classified with a different population. Okay. When we reject the null, we refer to this as statistical significance. Okay, so if p is less than your set alpha, you have statistically significant results. As a side note, I mentioned this in your activity last week, but anytime you see sig in a column in SPSS, that is a p-value. Okay, just take a mental note. Sig equals p. Sig equals the calculated p, not alpha. Okay. Every time you see a p-value, a null hypothesis has been tested. So the p-value is the evaluation of the null hypothesis. I can't say that enough. Tips. Keep track of your nulls so you know how to interpret your results. Once we start getting deeper into our statistical tests, there will be multiple null hypotheses that you have to remember that exist in the outputs. So we're not always just looking at the null hypothesis for a given test. A lot of times we also have to look at null hypotheses for assumptions. So again, anytime you see a sig column, you're looking at a p-value. Anytime you have a p-value, you have a null hypothesis that has been tested. What that null hypothesis is based on the test that the p-value is attached to. So keep track of your nulls. I usually tell students to write out, make a document of null hypotheses. I usually will give you tools that also have the nulls written out so that you have practice, seeing what they look like. And I usually will always give you a null hypothesis associated with the main test when we start getting into that section of the class. So keep track of your null hypotheses. Also know what you desire to find and what adjustments, if applicable, need to be made to the data. So if you violate an assumption, a lot of times you have to make an adjustment to the degrees of freedom or something within the calculation for the statistical test you're running. Okay, so knowing what you desire to find is another fancy way of saying know what your null hypothesis is, right? And what the contrast of that null hypothesis is. For assumptions, general rule of thumb for a class, usually you want a p-value greater than 0.05. Because if you have a p-value greater than 0.05, you accept the null hypothesis. And usually the null hypothesis of assumptions is that you have met the assumption. So if you get a p-value less than 0.05, that typically means you have violated an assumption and an adjustment needs to be made. For your statistical tests, such as t-tests, ANOVAs, ANCOVAs, MANOVAs, MANCOVAs, that type of stuff, the main tests what you're looking for is entirely dependent on what you're trying to prove. So it's good to remember, a lot of people kind of fixate on oh, we need a p-value less than 0.05. We need to know that the intervention worked. Sometimes it's not so much that you want stuff to be different. Let's say you're testing a new piece of technology or equipment and you want to see how it compares to kind of a gold standard of equipment. So maybe I make a new motion sensor to capture 3D motion, and I'm comparing it to a gold standard of, using a marker set with reflective markers. Okay. In that case, I would want my results to not be significantly different from each other because then I know that I have consistency in measurement between the two devices, right? So non-significant findings are oftentimes significant, right, in terms of their meaning. So the p-value that you desire is entirely dependent on what you're trying to find.